Hi, this is Dr. Tyagarajan. In this session, I am going to discuss about virtual memory organization. This part of the video explains how secondary memories are mapped with main memories. Now, let us see what is virtual memory. Virtual memory is a memory management technique in which the secondary memories such as hard disks can be addressed as though it were part of the main memory. Any program which is available in the secondary memory should be transferred to the main memory, then only it will be executed. This technique uses main memory as cache for the secondary storage. Cache means it is a small memory compared to secondary memory. But in the previous session, we discussed about cache. That cache is very small compared to the main memory. Here, compared to the secondary storage like hard disk, this main memory is small. So, if your program is very large, it should be stored in the secondary memory or secondary storage devices like hard disk, and part of that should be transferred to the main memory whenever it is needed to be executed. So what is the need for virtual memory? Users can run applications larger than main memory, and multiple programs can share the main memory efficiently and safely. The programs available in the secondary memory can be loaded anywhere in the main memory, and it is called as relocation. So how does it work? If the program is larger than the size of the main memory, actually the main memory is also called as physical memory, or the main memory is generally RAM. So if the program is large, then it is divided into pages, and all these pages will be stored in the secondary memory. And the page which is needed to be currently executed will be transferred to the main memory from the secondary storage device. Then the next page will be transferred to the main memory and execution continues. Because all the pages may not be directly stored in the main memory because the program is large. So the program is transferred part by part and executed. So the virtual memory organization method helps to act the main memory as a cache for a big program. Since large number of programs are stored in the secondary memory, that is hard disk, all those programs have to share the same main memory. That means first one program will be stored in the main memory, then second program will be stored, and that program will be read by the CPU for execution. Sometimes 2 or 3 programs will be simultaneously loaded into the main memory, and the CPU will execute one by one. That means in all these cases, the main memory is shared by many programs. Similarly, these programs also share the CPU and I/O devices. So, these programs should not interfere by reading from or writing into the areas of another program. So this requires some protection mechanism. The address issued to access the secondary memory, that is hard disk, is called as virtual or logical address. All these addresses form the virtual address space. So you know that the virtual address space is very large. The addresses issued to access the main memory is called as physical address, and all these addresses form the physical address space. The logical address space is very large compared to the physical address space. We have 16 GB RAM, that is physical address, but 1 terabyte hard disk in computers. That means it is the secondary storage. The larger virtual address is to be translated to physical memory's smaller address. This is called address mapping or address translation. The address of the secondary storage, that is virtual address, is broken into virtual pages. Each page has a page number. For example, we are using 32-bit processors. So 32 bits will be used for specifying the address. In those 32 bits, the bits 12 to 31 will be used to address the page numbers, and the remaining 12 bits, that is bits 0 to 11, will be used to address each location in the page. That means that is called as offset address. Anyway, this offset address will indicate the starting address of the page. The address of the main memory, that is the physical address or the RAM address, is also broken into pages. This page size is same as that of the logical memory's page size. Each page has a page number, but here you observe the number of bits used to indicate the page number will be 18 bits. So for secondary storage, 20 bits are used, but for main memory, only 18 bits are used to address the number of the page. But the offset is same. It is using 12 bits, right? So the page size in both main and secondary memories use 12 bits. Using these 12 bits, you will be able to address 2 power 12 locations or bytes. So 2 power 12 can be written as 2 power 2 into 2 power 10. This 2 power 10 is nothing but kilo, and this 2 power 2 is 4. So you can say that 4 kilobytes can be accessed using these 12 bits. So 12 bits means you can address 4 kilobytes of memory. So this size is common to both physical and logical memories. Page size is common. The number of pages in the logical memory, that is number of pages, not the page size here. How many number of pages will be there? Since we are using 20 bits, you can have 2 power 20 pages. Similarly, in the case of physical memory, you will have 2 power 18 pages because it is using 18 bits. Now you compare these two. Physical memory can have only 2 power 18 pages, but the logical memory, secondary memory, will have 2 power 20 pages. That means the main memory size is smaller compared to the logical memory or secondary memory size. When all pages in the main memory are in use, and if a new page is to be loaded from the secondary memory, then least recently used page is replaced by the new one. This is called LRU replacement scheme. If a valid bit is 0, then page fault occurs. In such a case, the operating system gets control and it finds the page in the next level of hierarchy, that is from the disk, and decides where to place that requested page in the main memory. Each time when the page is to be loaded from the secondary memory into the main memory, the page table has to be searched to know which page in the main memory is to be used. So this consumes more time because it has to search the complete page table. It is somewhat big table. So to speed up this process, translation look-aside buffer is used. This is the translation look-aside buffer. This is acting as a cache for this page table. If a reference is made to get the translated address, first we will search in the TLB. If it is available in this TLB, then it is a hit. So we will get the physical address from this TLB and the data will be loaded to the corresponding page in the physical memory. If it is not available, then it is a miss. If it is available, the reference bit will be set to 1. The valid bit will also be 1. If it is not available, then valid bit will be 0. In that case, the reference address should be brought from this page table. If the page table has that reference address, it should be loaded into TLB first. After that, we will get the reference address from this TLB. So if the reference address is available and when it is loaded here, the dirty bit will be set here during this write operation. If the page is also not available in this table, then it will be loaded from the secondary storage device.